Okay, good morning everyone. This is the next lesson in my Physics 20 course. Just a couple of quick notes to begin with before I get into it. If you were one of my Physics 20 students and you were watching this because you were absent from class during the presentation of the lesson, then you need to be aware that I had a problem with the recording of the lesson during class, and as a result I'm re-recording this outside of class. What that means for you is I'm going to be presenting this faster than I would be if I were in front of students. I don't need to worry about any questions that students are asking me. I don't need to worry about me asking students questions. And I certainly am not going to pause at certain points in this video to give students time to write things down. If you feel that you need to write something down and you have to pause the video, then by all means pause it. One more note, and this is to all of my students, regardless of whether you were in class or not, and also to anybody else watching, is in the course of this lesson, I'm going to be working on 4 different examples. And what we did in class, and it's the same thing I'm going to be doing here, is we did not complete those 4 examples. What we did is we set up the examples, we determined which formulas would be needed to complete the examples, and then I told my students that for homework, they need to complete the examples. So that's what's going to happen in this video. I will post another video that continues off of where we left off and has complete solutions, and I will post a link to that video with the completed solutions in the descriptions to this video once they're all posted. I think that covers it. Let's get started here. I call this 20.1.5 Part 2, the kinematics equations. We're going to be solving uniform acceleration problems algebraically using the kinematics equations. So these kinematics equations are equations that you are familiar with. We wrote a quiz recently where you had 3 questions to solve, and they involved uniform acceleration. We've had a couple of days of practice of solving these problems. And here are what I call the 5 kinematics formulas. Very briefly, you know that, and I've talked about this in class, you know that in terms of the formula in the top left corner, on your formula sheet it says average acceleration, but I've told you at this point in the course, that's the distinction we don't care about. Every acceleration we look at is uniform, it's constant, so we don't have to worry about the word average. You also know that I would prefer to use acceleration equals final velocity minus initial velocity over time. There are teaching reasons for that, and what I've tried to get you to understand as a student of mine is I think you're better off if you get used to looking at that formula instead of the one that's on your formula sheet. The other thing, and it's certainly a serious issue, is that the formula sheet that you're given, which is the formula sheet that comes out of Alberta Education, which you get for diploma exams in Physics 30, has that central formula, that Vf squared equals Vi squared plus 2AD, written so there are no vectors above the A and the D. And I don't know why Alberta Ed has decided to do that, but it's wrong. Okay, it's wrong. I know it's wrong because there are situations where you can use that formula, and if you don't take into account the vector nature of acceleration and the vector nature of displacement in that calculation, you will get the wrong answer. So you need to make sure that you put vector symbols above those, and I've directed you in class to put them above those variables in the equation on the formula sheet I've given you. There is no vector symbol above the velocity in this equation. It's not velocity, it's just speed, whether it's the initial or the final. And the basic reason for that, and I'm getting maybe a little ahead of myself, is that we are going to be assigning any vector a positive value or a negative value in these equations depending on what's happening. And when we have, say, Vf squared, well, it doesn't matter whether Vf as a velocity is positive or negative. When you square it, the negative would go away. So it's meaningless to put a vector symbol above there because it's not going to change things. All right, I hope that you've realized, and I've talked about it in class, every single problem we have done involves an object speeding up. We've talked about cars, traveling at 10 meters per second, accelerating forward, and reaching a speed that's greater. We've talked about objects which are thrown downwards towards the surface of the Earth. And in those two situations, the objects are speeding up. What we have not done is solve problems where the velocity is in one direction, or the motion, if you like, is in one direction, but it's accelerating in the opposite direction. If you have something that is accelerating opposite to the direction that it's moving, it's because there's a force acting on it opposite to the direction that it's moving. And as long as that force is continually applied, the acceleration will be continually experienced by the object. And as a result of that force being opposite, which means the acceleration is opposite, the object will slow down. And if that acceleration / force continues to be applied to the object, then not only will it slow down, but it will slow down to a stop. And further, if the acceleration is continually experienced, not only will it slow down to a stop, it will then stop and change direction and speed up in the opposite direction. Classic example of this is if you throw a ball in the air. Right? It's going to slow down until it reaches the top where it stops, and then it's going to speed up on the way down. This is what we're focusing on today. What we are focusing on today is situations where the acceleration is opposite to the direction of motion. And that's certainly going to change things. As I have already said, what's going to happen is every place there's a vector in one of those formulas, you need to put in a positive or a negative depending on whether the vector is positive or whether it's negative. Okay. Well, I want to review what we've already learned about displacement, velocity, and acceleration and what they mean when they're positive or negative. So what does a positive displacement mean? Everything I talk about in this chart, I'm going to be talking about objects that move vertically. I'm telling you that a positive displacement means that the object ends above where it started. Don't forget, displacement is change in position. So if the change in position is positive, it must end up further away from the surface of the Earth than where it started. If you have a negative displacement, that means the position has decreased. That means the object ends up below where it started. Now, if I were doing this lesson and I were not going to talk about vertical, but I wanted to talk about horizontal, I would say positive displacement is when the object ends up to the right of where it started, and negative is when it ends to the left of where it started. Positive velocity, we've talked about this a lot. Positive velocity simply means the object is moving in a positive direction. So the positive velocity in our scenario means the object is moving up, and a negative velocity means the object is moving down. Now we get to acceleration, which is tricky, because you're basically told in Science 10 that a positive acceleration means speeding up and a negative means slowing down. And we have to be more sophisticated in our understanding of things in Physics 20 and Physics 30. Positive acceleration does not necessarily mean the object is speeding up. What it means is the velocity is increasing. And I know that you might look at that statement and go, well, if the velocity is increasing, it must be speeding up. No, it doesn't have to be. I'm going to show you an illustration of what that means and why that comes about, but I'm going to use the negative acceleration to explain why these things don't necessarily mean the object is speeding up or slowing down. A negative acceleration means the velocity of the object is decreasing. Okay? It doesn't mean the object is slowing down. The object might be slowing down or it might be speeding up. All it means is the velocity is decreasing. So I'm going to ask us to imagine a situation where an object is thrown into the air, goes up to the top, stops, and then falls back down to the bottom. So we should know, of course, that when an object reaches the top of its vertical path, it has to stop, because if it's traveling up and then down, it has to change direction. Let's imagine that it starts with an initial velocity of positive 20 meters per second at that height. So that means at that point in time, it's moving up at that instant at 20 meters per second. Sometime later, it's going to be moving up at 10 meters per second. And then sometime later, it's going to stop. Don't worry about the spacing of these. The basic idea is that spacing between 20 meters per second and 10 meters per second is greater because during that interval, it would have been traveling faster, covering a greater distance. Doesn't matter though. After it stops, it has to change direction, which means at some point in time, it's going to be traveling down at 10 meters per second and then continue to speed up in that downward direction. So its velocity later will be negative 20. And for later, it might be useful to note that when it's moving up at 10 meters per second, it's at the same height as when it's moving down at 10 meters per second. I want us to compare these two velocities. Going from 20 meters per second to 10 meters per second is a decrease in velocity. If you take Vf minus Vi, you'll have 10 minus 20. You will get a negative delta V, which means the velocity is decreasing. The acceleration in this region is negative because the velocity decreases. If we compare going from 10 meters per second to 0 meters per second, we get a negative delta V as well. Delta V is final velocity minus initial. So I take 0 minus 10, I get negative. What about from 0 to negative 10? Well, the final velocity in that interval is negative 10. If I take negative 10 minus 0, which is the initial, I get a negative. And this continues. It doesn't matter which interval you're talking about. Your delta V will always be negative, which means the acceleration everywhere here is negative. Whether the object is on its way up, slowing down, or on its way down, speeding up, it still has a negative acceleration. And from now on, this is what we have to use. All right, so from now on, when we use the formulas, we'll have to consider the directions for those things that are vectors. Let's get into the examples. A race car is traveling at 140 kilometers per hour and it brakes suddenly, experiencing an acceleration in the opposite direction of its motion. I didn't have to tell you the acceleration is opposite. I could have just said it experiences an acceleration of magnitude 7.5 meters per second squared. And you should know it's opposite because we've all been in vehicles where the brakes are applied. Find the time it takes the car to stop and the distance traveled while it stops. So what do we know? Well, first of all, we have to convert that 140 kilometers per hour to meters per second. So we divide that by 3.6. That's our little thing that we have to remember. And you get 38.8 repeating meters per second, and we can toss that in our list. The car stops, which means Vf is 0. The acceleration is now negative. So this is what's different. Yesterday or the day before or prior to this, you wouldn't worry about negatives, but we have to put a negative in there. And of course, what we are asked to find is the displacement and the time. So what formulas do you use? Well, you can use a formula right now to find the displacement, and you can use a formula right now to find the time because you have enough information. What we said was that to find the displacement, we can use the following formula. You can use Vf squared equals Vi squared plus 2AD. And this is going to be, when I solve this with you in the next video, this is going to be a classic example of why you need those vector symbols above there. If you don't have them, it doesn't work. So this is going to be how you're going to find D. And once you find D, I suppose you could use pretty much 3 or 4 other formulas to find the time. That's not entirely true, but you have more options once you find D in order to find the time. However, what I would do to find the time, and it's just a personal preference, is I would use acceleration equals Vf minus Vi over t. And again, I'm going to solve those equations for the unknowns in the next video. So that's number one. Number two, a lawn dart is thrown straight up with a speed of 16 meters per second. Find the total time the dart is in the air and the maximum height reached by the dart. So I'm going to start off by saying that VI is 16, positive 16 because the dart is thrown up. And I'm going to play a little game here, a little trick. I'm going to say that VF is 0 because I'm interested in knowing what the maximum height is. And at the maximum height, the dart will stop. Okay? That's going to cause a bit of a problem in a bit for something, but we'll get back to that. The acceleration, of course, is 9.81 meters per second squared downward. The acceleration due to gravity is downwards because gravity pulls objects towards the surface. It accelerates them towards the surface whether the object is on its way up or on its way down. And if I find D now, that will be the maximum height because that corresponds to VF equals 0. If I use this list and I want to find time, I just need to be aware that that is just the time to the top. It is not the total time in the air. But due to the symmetry of motion, and it's because gravity is the same acceleration on the way up as on the way down, however many seconds it takes to get to the top will be the same as the number of seconds it takes to go from the top to the bottom. So I can take that time at the bottom of the screen and double it to get the total time in the air. So what formulas are you going to use here? Well, if you work on finding D first, which you probably would, I think. I guess I shouldn't say that. I probably would. I would be using the VF squared formula again. You don't have to do it this way. What you could do is find the time first using a different formula and then use that time along with, I don't know, VI and VF with a different formula to find D. Anyway, in order for me to find the displacement, the way I'm setting this up, I'm going to use this formula, and this formula becomes a little bit simpler because VF is going to be 0, and we'll come back to that. This will be very similar to the question we did in number 1, or we're going to do. Now, what would I do to find time? Well, I guess I could use acceleration equals VF minus VI over t. I could, and maybe just for kicks, I'll use a different formula here. How else can I find D? I could use displacement equals VFT minus 1/2 AT squared. And the reason why that's going to be useful to find time is since VF is 0, that VFT will reduce to nothing. Don't forget when we find that time, that will not be the answer to the question. We will have to double that time in order to get the answer to the question, which is how long is it in the air in total. Now, I don't know if those are the two formulas that I used in class. It doesn't matter. Because I said in class, as long as you're able to find the answer, that's what we care about. Question number 3. A bowling ball is thrown straight up from the edge of a tall building. It's 35 meters tall. With a speed of 10 meters per second, find the time the ball is in the air. So this is where things got more complicated. This is a very specific type of question that you need to get used to figuring out. And number 4 is going to be the same kind of thing. Well, let's make an itemized list first. VI is positive 10. The initial velocity is 10 meters per second up. We don't know VF. The acceleration due to gravity is negative 9.81 meters per second squared. And the displacement is going to be negative 35 meters. That's a fact. It doesn't matter that the ball goes up and then down. It's going to end up moving overall from the top of the building to the bottom. And if the building is 35 meters tall, then its displacement will be negative 35. And you're asked to find time. Now, if you follow my advice in class, which is that you look at this list of items and you notice that VF is not there. And you say, well, that means I do not want to find VF and I don't know VF, that means I cannot use an equation if it has VF in it. You whittle it down to the fact that you have to use the formula number 2 that you're looking at here. Displacement equals velocity initial times time plus 1/2 times the acceleration times time squared. So we can write that down. Displacement equals VI multiplied by t plus 1/2 times a times t squared. And if you're following along, I'm going to tell you right now what I told the class when we did this lesson. Write down that equation, but put your pen or pencil down at this point, because everything else that I write for a little bit, I'm going to erase. If you were to put in the numbers, and I'm going to not use units. You know at this point in the year that we're not using units in the formulas because it makes things too confusing, because you don't have a really strong math background yet in high school. I'm going to put in negative 35 equals VI, which is 10 times t, plus 1/2 times negative 9.81 times t squared. And this simplifies to negative 35 equals 10t minus 4.905 t squared. Well, the fact of the matter is, with the exception of, I believe, one student in the Physics 20 class this semester that I have, none of you know how to solve this equation because there's a t and a t squared in it. And this is something which we call a quadratic equation. And if you take Math 20-1 or even 20-2, you will learn how to solve this equation. But right now, solving this equation for t is outside of your grasp. You cannot do it. And that means that this equation, in this situation, is a dead end. You cannot answer the question using that equation. What we said instead is that your goal now becomes finding VF. So there's that wrinkle, but we're about to encounter another wrinkle. Because the formula we're going to use to find VF will be VF squared equals VI squared plus 2AD. So VF squared is equal to 10 squared plus 2 times negative 9.81. And now you're writing this down, by the way, times the displacement of negative 35. And we can calculate what we get for VF squared. And when we get VF squared, let's see what we get. So I have to take 10 squared, which is 100, plus 2 times negative 9.81 times negative 35, and get this number, 786.7. And then we take the square root. What do we get? Let's see. .28 meters per second. I'll carry all my decimals when I need to, but I'm just going to write down 28. And what I said in class, I wrote 28 here. I might have written 28.0 whatever, 04, let's see, 05 meters per second. And I said to the class, that is wrong. What's wrong with it? And everybody thought for a second, and I think it was Maxime who said, well, the final velocity is actually negative because the object will be moving down when it strikes the ground. And that's exactly right. And I took that opportunity to teach you a little tiny thing about taking square roots as soon as you get to grade 11 and beyond. It's not just the square root, it's plus or minus the square root. I mean, if I square 28.05, I will get VF squared. If I square negative 28.05, I will get VF squared. So when we look at this part here that I'm going to highlight in yellow, and I'm into a math kind of lesson right now. When you look at that, it's pronounced plus or minus, and that means literally what I've just said. It means that VF can be plus or minus. And you have to decide which one it is. Anyway, at this point in time, you now have VF, VI, A, and D. So to find the time, I would recommend using the acceleration formula. Acceleration equals VF minus VI over T. And that's what you would do to find the time for example 3. Take a look at example 4. Example 4 is very similar to example 3, except there's an added wrinkle. So remember, with example 3, you ended up with a formula that you didn't know how to solve for t, so you found VF first, and then you have to remember that VF can be positive or negative. So let's go through this one now together. A heavy object is thrown upward with an initial speed of 45 meters per second. I know that's kind of cartoonish. Nobody's going to throw a safe in the air upwards at 45 meters per second. That's pretty fast, and the safe is pretty heavy. How much time has elapsed when this object is at a height of 20 meters? So let's just follow the math here. VI is positive 45. VF, we do not know. We're not told what it is. The acceleration due to gravity is negative 9.81 meters per second squared. The displacement is positive 20. We want to know when it is at a height of 20, which means it's 20 meters above where it started, which means the displacement is positive 20. When I say we want to know when, that means we want to know the time. But we run into a problem here, and you don't have to write down what I'm about to write down. The problem is we're back to that d equals VIT plus 1/2 AT squared, and if you put the numbers in, you're going to be left with an equation in which you have to find t, but there's a t and a t squared and you don't know how to do it. So what do you do instead? Well, what you do instead is you find VF. Now, I'm not going to find VF. That's going to be your job. But there is an added wrinkle here. You are going to use VF squared. You are going to use VF squared equals VI squared plus 2AD. You're going to put in VI, A, and D. You're going to get VF squared is equal to some number. And then you're going to go VF is plus or minus the square root of that number. And then I would ask you to think about, well, is it plus or is it minus? And what we discussed in class is when you throw an object into the air, it goes up and then down. So if it reaches a height of 20 meters, there are going to be 2 points in time when it's at that height. So when I say when is it at that height, or how much time has gone by when it's at that height, we're going to have whatever time this is, and then we're also going to have whatever time that is. We're going to have 2 times, which means this problem, this question is going to break into 2 problems. It's going to break into using the acceleration and VI and VF equals the positive to find the time, and VF equals negative of whatever that number is, along with VI and the acceleration to find the time. And that's how you would set up problem number 4. So once again, I'm going to post a link to a video where I complete these solutions in the description to this video.